In this final video for Chapter 12, we're going to talk about catalysis. So, let's begin with the obvious question, what is a catalyst? A catalyst is a substance that increases the rate of a chemical reaction. A catalyst is a substance that is consumed in an early step of the reaction, but it is regenerated in a later step in the reaction, so when you add the elementary steps together to get the overall balanced equation, it cancels out, and it does not appear in the overall balanced equation. So a catalyst is not involved in the stoichiometry of the reaction, it simply accelerates it. So how does a catalyst work? Very straightforward, by providing an alternative pathway or mechanism for the reaction that has a lower activation energy. Okay, so it's a completely different pathway that has a lower activation energy, and thus, since the activation energy is lower, that results in a greater value of K at a given temperature. What types of catalysts exist? They're generally grouped into two categories. Homogeneous catalysts are catalysts that are in the same phase as the reactants and products, and usually that means everything is in solution. But there are also heterogeneous catalysts, in which the catalyst is in a different phase or physical state as the reaction, and usually a heterogeneous catalyst is solid while the reaction is taking place in the solution or gas phase. So here's a diagram, shows a reaction profile for a chemical reaction. We can see for this reaction delta E is positive, but of course that doesn't matter. We don't care about delta E in kinetics problems. The uncatalyzed pathway is represented by the red curve, and you can see that the activation energy is pretty high. The energy of the transition state or activated complex is way up there towards the top. But the catalyzed pathway has a lower activation energy, as indicated by the blue curve, and therefore it has a greater value of the rate constant, and the reaction occurs more quickly. Now, let's compare these in terms of a distribution curve. In the previous video, we saw a distribution curve that shows how the number of collisions that occur with a specified energy varies as a function of energy. This is sometimes also called a Boltzmann distribution curve, and we can see on the x-axis we have a value of energy corresponding to the activation energy for the uncatalyzed reaction. The area under the curve represents those collisions that occur with energy equal to or greater than the activation energy and therefore result in reaction. Those are called effective collisions. So what happens when we add a catalyst and provide an alternative pathway with a lower activation energy? Well, you can see what happens. Moving the activation energy to a lower value without changing the distribution curve, because remember we're not changing the temperature, results in a greater number of effective collisions and therefore more reaction taking place and therefore a faster reaction. Here's an example of heterogeneous catalysis. Hydrogenation of ethene, also known as ethylene, C2H4. We're simply adding a molecule of dihydrogen across the carbon-carbon double bond, making it a carbon-carbon single bond. Now, the uncatalyzed mechanism requires breaking of the hydrogen-hydrogen bond to form two hydrogen atoms, is indicated by H dot. Addition of one hydrogen atom to the ethene molecule to form this odd electron species. That occurs very rapidly. And then addition of the second hydrogen atom to form the ethane molecule. The reason this is very slow is because the first step, which is the rate determining step, is extremely slow, given the fact that the hydrogen-hydrogen bond energy is quite high. Okay? However, using a catalyst, namely a platinum surface, we can speed the reaction by providing an alternative mechanism that has a lower activation energy. And here I have a diagram that illustrates the mechanism. This reaction takes place on the surface of platinum. Okay? So if I start over here, we can see that a hydrogen molecule comes down onto the surface of the platinum, as illustrated by that rectangular thing, and adsorption occurs. Essentially, the hydrogen-hydrogen bond breaks quite rapidly and quite completely, and the two hydrogen atoms bond to the surface of the platinum. They actually form covalent bonds to platinum metal atoms at the surface. In the second step, an ethene molecule also adsorbs onto the surface, and as, oops, I don't want to do that. Okay, and as you can see, it forms two carbon-platinum bonds. Okay, now it's very easy for one of these hydrogen atoms simply to migrate over and form a bond to the carbon, form the CH3. The second takes place, we form another one. Now the ethene molecule comes off, and you regenerate the metal catalyst. So the metal catalyst is neither produced nor consumed, it simply hangs out there. here's a question. We can decompose ammonia to its elements using two different metal surfaces as heterogeneous catalysts, and we're going to look at the activation energy for the reaction with these two catalysts at a given temperature. For tungsten, the activation energy is 163 kilojoules per mole. For osmium, 197 kilojoules per mole. The uncatalyzed reaction has an activation energy of 335 kilojoules per mole. So we can see that these two catalysts each lower the activation energy quite substantially. So, which surface is the more effective heterogeneous catalyst for the decomposition of ammonia, and why? Well, clearly it would be tungsten, because it has a lower value of the activation energy and therefore a higher value of the rate constant. Okay? More effective catalyst makes the reaction go faster. Here's a final interesting question that really is kind of advanced. The decomposition reaction on the two surfaces obeys a rate law that is first order in ammonia and inverse first order in hydrogen. What does that mean? Well, obviously it means that as the concentration of H2 increases, the rate of reaction decreases. How could we explain that? Well, if you go back and look at our mechanism for the surface catalysis of the hydrogenation of ethene, you will see that when hydrogen is exposed to the surface of the metal, that it occupies catalytic sites. It takes up space on the surface of the catalyst, and therefore there are fewer active sites for the reaction to take place. So it must be that H2 blocks active sites on the metal surface, therefore slowing the reaction. Okay, that's about all I have to say about catalysis.